कर स्नान सिमर प्रभ अपना, मन तन भये अरोगा. After taking your cleansing bath, remember your God in meditation, and your mind and body shall be free of disease. Unit 3, Classification of Elements and Periodicity in Properties. Part 2 by Amrik Singh, PGT Chemistry. Atomic radius. It is the distance from the center of nucleus to the outermost shell of electrons, as shown in the diagram. We have nucleus at the center and outermost shell of electron, that is atomic radius or atomic size. We have seen the nucleus, electrons. Atomic radius again, it is the distance from the center of nucleus to the outermost shell of the electron, as is clear from the diagram. Practically, it is not possible to isolate each atom and to note its atomic radius. However, an estimate of atomic radius can be made by knowing the distance between the atoms in the combined state. For example, covalent radius. It is the half of the distance between the center of two atoms when they are bound together by a single bond in a molecule. For example, bond distance in chlorine molecule Cl2 is 198 picometer, and half this distance 99 picometer is taken as the atomic radius of chlorine. Let us have the explanation by we have one chlorine atom, second chlorine atom, they are overlapping and forming Cl2 molecule. The distance between their two nuclei is d, and covalent radius will be equal to d by 2. That is, it is the as given in the definition, covalent radius is the half of the distance between the centers of two atoms when they are bonded together by a single covalent bond, या single bond in a covalent molecule. Metallic radius, again type of radius is metallic radius. It is the half of internuclear distance separating the metal cores in the metallic crystal. Example, the distance between two adjacent copper atoms in solid copper is 256 picometer. Hence, the metallic radius of copper is assigned a value of 128, half of 256. Let's have the diagram. We have two copper atoms, and the distance between two centers is interatomic distance, and the half of this value is known as metallic radii as shown in the diagram. Note number 1. For simplicity, we use the term atomic radius to both covalent and metallic radius depending on whether the element is a non-metal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. Variation of atomic size or radius in periodic table. Atomic size generally decreases across a period. As for the element of the second period, it decreases on moving left to right. What is the reason? It is because within a period the outer electrons are in the same valence shell, and the effective nuclear charge increases as the atomic number increasing, resulting in the increased attraction of electron to the nucleus. Let us see the diagram. I have here atomic number third at the first in the first diagram with atomic number third, that is lithium, 3 proton and 3 electron, and they have inward pull, that is Z, and inner two electron act as screen for outer electron, that is screening effect. Z effective net inward pull will be Z effective will be Z minus S. Now if I move from lithium to beryllium, beryllium have atomic number 4, therefore their nuclear charge will be increased to 4 from 3 to 4, but the number of electron will be 4, 2 in the inner and 2 will be in the outer. Shell is here also second shell, main shell is second. The effective nuclear charge is increasing due to increase in uh, inward pull by the nucleus, because here the inward pull it was plus 3 in lithium and plus 4 in beryllium now. And in the same way boron plus 5, and size will decrease. On moving left to right, size decreases due to increase in effective nuclear charge. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number. Reason for alkali metal and halogen, as we move down the group, the principal quantum number n increases, value of n increases, and the valence electron are farther from the nucleus. This happens because the inner energy level are filled with electrons, which serve to shield the outer electron from the pull of nucleus. Shielding is increasing down the group. Consequently, the size of increases as reflected in the atomic radii. Down the group size increases because n increases, number of inner electron increases. This will increase the screening, and effective nuclear charge will decrease on the outermost electrons, and size increases on moving down the group. Effective size increases down the group due to decrease in effective nuclear charge on moving down the group due to increase in number of shells. Let us see, I have in the first diagram there are two shells. Now third shell is introducing, number of shells are increasing. Here first shell, second shell, third shell, fourth shell. Number of shells are increasing down the group, size is also increasing. Note, the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii value are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of the other elements. Ionic radii, the removal of electron from an atom result in the formation of a cation, where the gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cation and anion in ionic crystals. Note number 1. In general, the ionic radii of element exhibits the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons, while its nuclear charge remains the same. Second number, the size of anion, means having negative charge, will be larger than that of the parent atom because the addition of one or more electron would result in increased repulsion among the electrons and a decrease in effective nuclear charge. Let's clear it with the help of a diagram. I have oxygen atom at the center. 8 positive is there and 8 electron are there. 8 positive, 8 negative, 8 electrons, 8 protons. Now if I am adding one electron, now charge, central charge, nuclear charge is same in anion, but electron are 9. Electron increasing, therefore repulsion is also increasing and size is increasing, effective nuclear charge is decreasing. For and if I am removing one electron, From oxygen atom, it will have central nuclear charge will be 8, but number of electron will be now 7 in cation. Now effective nuclear charge becomes more for each electron. Now size will be less as shown in the diagram here. Oxygen atom, oxygen cation, oxygen anion. Anion is bigger than the parent, and cation is smaller than the parent oxygen. When we find some atoms and ions which contain same number of electrons, we call them isoelectronic species. Isoelectron means same number of electrons. Oxygen having atomic number 8, but here is O2 negative, 2 electron are added, 8 plus 2 10. Fluorine is having atomic number 9, but 1 negative charge, electron number 10. Sodium having atomic number 11, but 1 positive, number of electron are 10. Mg2 positive, atomic number 12, but 2 positive charge is there, number of electron 10. Have the same number of electron 10, therefore these species are called isoelectronic species. Their radii would be, point number 5, their radii would be different because of their different nuclear charges. The cation with the greater number of charge will have the smaller radius because of greater attraction of electron to the nucleus. Now atomic number of magnesium is 12. 12 means 12 positive charge. It will have the smaller size. Now sodium plus 11, fluorine 9, oxygen 8. Size of oxygen will be highest, then turn will come from fluorine, then sodium, and then magnesium. Point number 6, anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electron will outweigh the nuclear charge and ion will expand in size. Now, ionization enthalpy. It represents the energy required to remove an electron from isolated gaseous atom in its ground state. The ionization enthalpy is expressed in kilojoule per mole. The second ionization enthalpy is the energy required to remove the second most loosely bound electron. Let us understand this concept with the help of an animation. I have an atom, an electron, and at the center at nucleus, there is an electron which is revolving around the nucleus. Yes, electron is revolving in its orbit, and I have some source of energy, and photon strike this electron and provide the energy to this electron, and this electron is ejected. That is the ionization energy, minimum amount of energy required to remove the most loosely bound electron from an atom is called a ionization energy. Suppose I have X atom in gaseous state, isolated state, then I have provided the ionization energy, then X will be changed into cation in gaseous state, and one electron will be removed. Note, energy number 1, energy is always required to remove the electron from an atom, and hence ionization enthalpies are always positive. The second point number second, the ionization enthalpy will be, second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second, and so on. The term ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. Variation in periodic table. Variation of an ionization enthalpy in periodic table. First ionization enthalpy generally increases as we go across a period and decreases as we descend a group. Left to right ionization energy increases and top to bottom in a group it decreases. Reason: to understand these trends, we have to consider two factors: the attraction of electron toward the nucleus, the repulsion of electron from each other. The effective nuclear charge experienced by valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by intervening core electron. In general, shielding is effective when the orbital in the inner shell are completely filled. Z effective will be equal to Z minus S. Point number A, explanation A, across a period, increasing nuclear charge outweigh the shielding. Consequently, the outermost electron are held more and more tightly, and the ionization enthalpy increases across a period. In other words, shortly we can say that on moving left to right in a period, the effective nuclear charge increases, therefore ionization energy also increases. As we go down the group, outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electron in the inner levels. In this case, increase in shielding outweighs the increased nuclear charge, and the removal of outermost electron require less energy down the group. As we move down the group, effective nuclear charge decreases. In shortly, we can say that's why ionization energy also decreases. Yes, note number one, when we consider the same principle quantum level, an S electron is attracted to the nucleus more than P. We have some exception. We are discussing the exception number one. For example, beryllium atomic number is 4 and boron atomic number is 5. As we left to right, ionization energy should increase. If we move 4 to 5, ionization energy should increase, but it is not happening. The ionization energy is boron is less than beryllium atomic number 4. In beryllium, the electron removed during the ionization is an S electron, outermost is the S electron. The electron removed during the ionization of boron is a P electron. Beryllium, S electron has to be removed, and in boron, P electron has to be removed. The penetration of S electron, 2S electron to the nucleus is more than that of 2P electron. 2S electron are more closer to nucleus than P electrons. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electron than the 2s electrons of beryllium. Therefore, it is easier to remove 2p electron from boron compared to the removal of 2s electrons from the beryllium. Thus, boron has smaller first ionization enthalpy than beryllium. Beryllium is group 2, boron is group 13. Therefore, group 2 should have lower ionization energy than group 13, but it is not like that. Group 13 have lower, group 2 have more ionization. Exception is there. And answer, in group 2, electron is to be removed from S orbital, and in group 13, electron is to be removed from p orbital. P is away from the nucleus, S is near to the nucleus. Therefore, uh, removal of electron in group 2 is difficult, and in group 13 is easy. Note number 2, another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. Oxygen Oxygen is atomic number 8 and nitrogen is 7. 7 to moving 8, ionization energy again should increase, but it decreases. And if we want to answer these questions, then we will have to write the electronic configuration. In the previous case also, there is an anomaly of beryllium and boron. We write the electronic configuration, we will get the answer. Here there is anomaly of oxygen and nitrogen. We just write the electronic configuration first and we will get the answer. In nitrogen, p orbital is half filled. Half filled and completely filled orbital are very stable, and the removal of electron is very difficult in case of nitrogen family, while in case of oxygen family, last p subshell is not half filled, therefore electron can be removed with ease. And another explanation is there in the NCERT, that this arises because of the nitrogen atom, 3 2p electron reside in the different atomic orbital, where in the oxygen atom 2 of the 4 2 electrons, the 2p electron must occupy the same 2p orbital, resulting in an increased electron repulsion. That in oxygen 2p electrons are in the same p orbitals, and they will cause the repulsion. Consequently, it is easier to remove the 4 2p electron from oxygen than it is to remove one of the 3 2p electrons from the nitrogen, and hence the anomaly. Electron gain enthalpy. When an electron is added, it is reversed to ionization enthalpy. When an electron is added to a neutral gaseous atom X to convert into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy. Electron gain enthalpy or electron affinity. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion as represented below. X is the atom in gaseous state, isolated atom adding one electron changing into negative ion gaseous state, and energy change is going on. Electron gain enthalpy delta electron gain enthalpy will be negative depending on the element. The process of adding an electron to atom can either be endothermic or exothermic. Now, variation in periodic table. The variation in electron gain enthalpies of element is less systematic than the ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in atomic number across a period. It becomes more negative as we across a period. That is, the tendency to accept the electron becomes more as we move left to right. Reason: the effective nuclear charge increases moving left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to positive charge nucleus. Electron gain enthalpy become less negative as we go down the group because the size of the atom increasing and the added electron would be further from the nucleus. Note, there is an anomaly. Again, there is exception. Electron gain enthalpy of oxygen, fluorine is less than the succeeding element. Oxygen down the group, electron gain enthalpy should decrease, but after oxygen we have sulfur. Sulfur has greater, and after fluorine we get chlorine. Next element is chlorine. Therefore chlorine should have lower, but it is more, it have more electron gain enthalpy, more negative value of electron gain enthalpy. This is because when electron is added to oxygen or fluorine, the added electron goes to the smaller n is equal to 2 quantum level and suffer significant repulsion from other electrons present in this level. For the n is equal to 3 quantum level, sulfur or chlorine, as in case of oxygen family or fluorine halogen family, that electron occupies a larger region of space and the electron repulsion is much less. Again, the answer is given by electronic configuration. Just write the electronic configuration of oxygen and sulfur, and then for the next case is fluorine and chlorine. We will get the idea of the answer. Electronegativity, a qualitative measure of the ability of an atom in a chemical compound to attract the shared pair of electron to itself, is called electronegativity. It is the ability to attract the shared pair of electron toward itself by an atom in a molecule. Unlike ionization enthalpy, electron gain enthalpy, it is not measurable quantity. However, a number of numerical scales of electronegativity of element with Pauling scale, Mulliken scale, Alfred Rocco scale have been developed. Linus Pauling, an American scientist in 1922, assigned the arbitrary value 4.0 to fluorine, the element considered to have the greatest ability to attract the electron. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that hold a pair of atoms together. Variation, it is variation. Electronegativity is inversely proportional to atomic size, and in same ionization energy also have the same variation. Electron gain enthalpy also have the same variation. All these three quantities are inversely proportional to atomic size. Periodicity or balance or oxidation states. The valence of a representative element is usually, though not necessarily, equal to the number of electrons in outermost orbitals, or a equal to 8 minus the number of outermost electron. Nowadays, the term oxidation state is frequently used for valence. The oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in a molecule. Anomalous property of second period elements. Second period are these, I have first period is hydrogen helium, and second period is lithium beryllium boron carbon nitrogen oxygen fluorine neon. The first element of each group, lithium, beryllium, and group 13 to 7, boron to 4, differ in many respects from the other members of the respective group. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group: magnesium and aluminium, that is magnesium and aluminium respectively. This sort of similarity is common referred to as diagonal relationship in the periodic properties. The anomalous behavior is attributed to their anomalous behavior is shown, small size, okay, large size or radius ratio, high electronegativity, absence of d orbital in valence shell, ability to form p pi multiple bond. Okay, second one, if someone is showing the difference in the properties in the top one, there will be four main reasons: small size, high electronegativity, absence of d orbital in valence shell, and ability to form p pi bond in second period. These are the reason for anomaly. Okay, anomalous behavior. Nomenclature. Both American and Soviet scientists claim the credit for discovery of element 104. The American named it Rutherfordium, whereas the Soviet name is Kurkotvium. To avoid such problem, the UPSC has made recommendation that until a new element discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element as shown below. Digit, name and abbreviation: 0 for nil, 1 for un, 2 for bi, and 3 for tri, 4 for quad, 5 for pent, 6 for hex, 7 for sept, 8 for octet, 9 for n. And the symbols are also N, U, B, T, Q, P, H, S, O, E, and these are the symbols, respective symbols. And we have the some name also written. Atomic number 101 is for un. We read in the first table, and 0 is nil, and 1 again for un, and em is added by, and the name will be given un nil un em, u for un, and n and u for un, n for nil, and u for again un. 101, 102, 1 is un, 0 is nil, and 2 is bi, and em is added. I, single I will come here. 103, 1 is un, 0 is nil, and the 3 is a try again em. Try note the 2 I, single I will be there. In this way we can write name of the all these elements. Official, if there are the star is given in the table. IPSC name yet to be announced, element yet to be discovered. For plus, element is yet to be discovered, and for star, the element discovered, official name is not yet announced. Thus, new element first get a temporary name with a symbol consisting of three letters, later permanent, and the symbol are given by the vote of the IPSC representative from each country. The permanent name might reflect the country or the state of country in which the element was discovered, or the pay tribute to the notable scientist. As of now, element with the atomic number 112, 114, and 116 have been discovered. Element with atomic number 13, 113, 115, 117, and 118 are not yet known. We have homework as well. We can do these questions. Answers are also provided. कोट भिगन हीरे खिन माहे, हर हर कथा साध संग सुनाहे. Millions of obstacles are removed in an instant for those who listen to the sermon of the Lord, Har Har, in the Sad Sangat. the company of the holy. Thank you for watching. Okay.